Hello there. I am Sambit Sahu. If you have been following the news, you know that there are a few vaccines for COVID-19 that are coming up and are showing great promise. There is a lot of discussion about how good these vaccines are. In this video, I'll explain how vaccines are evaluated and how we know how good they are. So what is vaccine efficacy? Simply put, it means how well does a vaccine work? One may think that it means how much will a vaccine protect me as an individual, but it actually doesn't imply that. It means how much does the vaccine protect the vaccinated population, not an individual. Epidemiologists usually use two terms when describing how well a vaccine works. The first one is efficacy, where the results are typically obtained from ideal conditions like in a clinical trial. The other term that is used is vaccine effectiveness, where the results are actually obtained from the real world. The design of these vaccine trials in scientific terminology is called a randomized controlled trial. It essentially has two study groups. In one group, all the participants get the candidate vaccine, and in the other group, everyone gets a placebo, which could be something as simple as saline water. There are a couple of important things that make a randomized control trial a randomized control trial. First is the allocation is random, so a participant cannot choose to be in a certain group, and a doctor also cannot decide to allocate a certain participant into one or the other group. It's done randomly by using a computer generated sequence. And the second aspect is that this allocation is also blinded until the end of the trial. So as a participant, you do not know if you received a vaccine or the placebo, and even your doctor will also not know what you got. So let's look at the two COVID-19 vaccine trials. The Moderna trial was conducted using 30,000 participants in the United States. There were 15,000 participants in each group. At the end of the trial, they found that 5 of 15,000 who were vaccinated got the infection, whereas 90 of 15,000 who were not vaccinated got the infection. In the Pfizer BioNTech trial that was conducted in several countries using a larger number of participants, 43,000, they didn't actually disclose the exact number of participants in each group, but for the purpose of this slide, I'm assuming they were identical, so 21,500 in each group. And they report that 8 of the participants in the vaccinated group got the infection, whereas 162 participants in the unvaccinated group got the infection. So let's crunch some numbers. The risk of getting infection in the unvaccinated group was 90 of 15,000, which is 0.6%, and the risk of getting the infection in the unvaccinated group in the Pfizer BioNTech trial was 162 over 21,500, which is 0.75%. Similarly, the risk in the vaccinated groups were 5 over 15,000 in the Moderna group, in the Moderna trial rather, which is 0.03%, and 8 of 21,500, which is 0.04%. Now, vaccine efficacy is calculated using this formula, RU minus RV over RU. What it essentially means is the relative reduction in risk of getting infected if you receive the vaccine. So using this formula, you get the vaccine efficacy of 94.4% for the Moderna vaccine and 95.1% for the Pfizer BioNTech vaccine, which is pretty close, if not identical, to the numbers that are reported in the press release from these companies. Now, there are some other outcomes, some other numbers by which you can also measure how efficacious these vaccines were. Vaccine efficacy was more about relative risk reduction. There is also absolute risk reduction, which is simply the difference between the two risks in the vaccinated and the unvaccinated group. So RU minus RV in the Moderna trial gives you zero point 0.6 minus 0.03, which is 0.57%, and similarly 0.71% in the Pfizer BioNTech trial. Essentially, this means that you had a 0.6% risk, or participants had a 0.6% risk of getting infected if they were not vaccinated. They had a 0.03% risk of getting infected if they were vaccinated in the Moderna trial. So the absolute reduction in risk was 0.57%. Another number you can generate from this absolute risk reduction is its inverse, which is also called the number needed to vaccinate, or NNV. So 1 over 1 over 0.57% in the Moderna trial gives you 176, and 1 over 0.71% gives you 140. So this essentially means that you need to vaccinate 176 persons with the Moderna vaccine to protect one individual from getting infected. Similarly, with the Pfizer BioNTech vaccine, you need to rather vaccinate 140 individuals to protect one person from getting infected. One thing to remember when looking at vaccine efficacy results from these vaccine trials is that these trials are conducted in very controlled clinical conditions. They generally have pretty strict selection criteria. Furthermore, only a certain select kind of people will generally enroll in such trials. These trials are conducted in select participating institutions which generally have pretty good infrastructure. So we really don't know if if the kind of efficacy that is achieved in these trials can be achieved in the community. There is a term called vaccine effectiveness, which has been used to uh, know how effective a vaccine is in the community. It's defined as the extent to which a vaccine prevents disease among vaccinated persons in the community. So there is another term which is called community effectiveness, which is defined as the extent to which a vaccine prevents disease among all persons, both vaccinated and unvaccinated in the community. It's a simple mathematical formula, which is it's a product of vaccine effectiveness times the percentage of population that is vaccinated, or the vaccine coverage. So more people that are vaccinated in a country or in a population, you achieve higher community effectiveness. So vaccine effectiveness in a community can really be different from vaccine efficacy that is observed in a clinical trial, because of multiple factors that can be at play in a community that are not really or necessarily present in a clinical trials controlled environment. For example, the disease burden. If you look at infection rates in the US, it's 3.77% since the start of the pandemic. Compare that to the infection rate in the unvaccinated groups in the two clinical trials. The infection rate in the US is 5 to 6 times higher than in those trials. If you also look at the timing of the trials, these trials were conducted around June to August, September, when the case rates were relatively lower compared to now. So with increased disease burden, we can expect that the vaccine's effectiveness could also be different. Vaccine effectiveness can also be influenced by healthcare access that can differ in the community compared to how it was during the clinical trials. It can also be influenced by viral mutations. If the coronavirus undergoes any mutations in the future, the effectiveness of the current vaccine will definitely change. It can also be influenced by vaccine coverage, which is essentially the percentage of the population that receive the vaccine. And it can also be influenced by any development of herd immunity. Herd immunity is a pretty interesting concept. It's defined as the cumulative social effect of vaccination. So this is a social effect as opposed to any biological effect that is measured by vaccine efficacy or effectiveness. So this is defined as a cumulative social effect of vaccination, because a vaccinated person not only protects himself or herself, but also others, because this immunized person can no longer be a potential transmitter of the virus. This is shown in this cartoon on the right. So this shows the population is divided into sort of three groups. There is an infected person who is shown by a red dot, a healthy person is shown by a white dot, and a healthy vaccinated person is shown by a blue dot. So in the scenario on the left, which shows a low immunization rate, uh, there are 20% of the people are vaccinated. So there are a total of 100 dots. It's a 10 by 10 matrix. So 20% of them are vaccinated with a blue dot. There are three persons who initially were infected. They're shown by three red dots. And the rest of the whites are the people who are healthy but not vaccinated. So in the scenario on the left, which shows the low immunization rate of 20%, you see that the three initially infected persons, they infect another 8 more, so a total of 11 persons get infected. Now in the high immunization rate on the right, you have 80% of the people who are vaccinated, and so the same three persons who are initially infected, they can only infect one more person, so we have a total of 4 infections. So even if there are several more healthy unvaccinated persons, they don't get infected if a large proportion of the population is immunized, because these immunized persons form sort of a barrier around the infected person and prevent the transmission of the disease. This can be also shown in a very cool illustration animation in the next slide. Here, each infected person is shown by a black dot, an unvaccinated person is shown by a blue dot, and a vaccinated person is shown by a yellow dot. And you see 6 different scenarios. The first one is on the top left is when no one is vaccinated, and gradually you have 25, 50, 75, 90, and 95% of the population vaccinated. And you can see how the disease progresses in the different fields. So you can see that when in the same amount of time, how the disease progresses in the 6 groups. The red lines show the spread of the infection. It happens at a much rapid rate in the top left group, where more and more persons are infected, whereas in the populations with higher rate of vaccination, you can see that the spread is limited, because all these yellow dots, they prevent the spread of the infection. Now, this is a pretty cool concept that a lot of people don't understand, but you can see this is why more and more people need to be vaccinated to control a disease. Specifically, this can also be useful when the vaccine itself is not very efficacious. So you can achieve more by having more people vaccinated. So this is all in this talk. If you have any questions, please write your questions in the comments below, and I'll be back with more videos in the future. Thank you.